before I have a bunch of examples in a file on Blackboard that is called single sample t-test manual calculations. They're not actually all manual. The last couple use SPSS or Excel for the calculations, but most of them are manual calculations. We're going to go through them now. Before we get to that, I want to clear a few things up about this idea of what T and what Z are. Okay, so for starters, if we want to compare two groups, if we want to get a judgment as to how different two samples, two groups, two populations are, the variability within the groups has a lot to do with it. So for instance, if I told you that I was measuring the average temperature of 12-year-old boys, and I found the normal temperatures, say 98.6 average for the entire population of 12-year-old boys. I took a sample and I found that the average for that particular population, for that particular sample, was 96.9. Not much of a difference, 96.9, 96.8, pretty much the same thing. In fact, the worst case you would expect was 5 degrees in either direction, 5 degrees lower, 5 degrees higher. That would be a big difference, right? That would be very low temperature, very high temperature. Same 12-year-old boys. I take that same sample, except this time I'm concerned about their weights, right? And I look at their weights average 100 pounds. Well, now, if I told you that the population average, say 12-year-old boys 100 pounds, tell you for our sample, the average weight is 95, say, gee, that same 5-pound difference really doesn't mean very much anymore. With temperature, it meant a lot because temperatures, the variability in all of the temperatures is not very great. But the weights could be a lot larger. The range of weights could have been 60 pounds to 150 pounds, for instance, a much wider range. So it's hard for us to compare or test whether two groups are the same or different by just looking at the numbers. Mean cholesterol level for heavy drinkers in a sample we take is 200. Mean cholesterol level for a sample we take in non-drinkers is 180. Well, the difference is 20, but we really don't know how important that difference is. But there you go. We don't really know. Don't worry about it. I do it myself all the time. We really don't know how important that 20 cholesterol milligrams per deciliter number is without knowing how variable cholesterol levels are. Could they vary? If they vary from 150 to 250, that difference of 20 is much more important than if they differ from 50 to 5,000, let's say, right? So using just the raw number doesn't help us that much in statistics. What we do instead, we look at it from the perspective of number of standard deviations apart. So we know, because we've been working with the z-table, that when we take a sample from a population, if it's normally distributed, that we can predict, if we know what standard deviation in that population is, if we have all those numbers, we calculate a sigma or standard deviation, we know that we can say that 95% of those people are within a certain range of the middle of that population, the mean of that population, right? 95% of them are within 1.9 standard deviations, which we can calculate from the population below the mean, and 1.9 standard deviations above the mean, right? So if I pick out one random individual, and that random individual's weight is 110, and I say to myself, well, let me compare that to the rest of the population. The mean is 150. I don't really know where I stand, do I, in terms of like where he is in that population. But if I knew that the standard deviation, that the standard deviation for that population, sigma, was 20, 110, 50, that's 2 standard deviations below the mean, his weight. So now I know that he is in the lowest 2.5% of that population. right? If he had been, what I said, 150, if he had been 190, he would be in the highest 2.5% of that population. That's the way that we use the z-score. The z-score is really a measure of the number of standard deviations. This is great when we work with a population and we know it's normally distributed. But now when we work with samples, because the sample size impacts the variability, the new standard deviation for a sample that we take is the standard deviation of the population over the square root of the sample size. The bigger the sample size is, the smaller is the standard error, the standard deviation of the samples that we take. Same deal. If we take a sample size 25, we can figure out what the standard error is from, if we know sigma, and we can figure out that, let's say that the sigma is 100. No, maybe not 100, make it smaller. Say sigma is 50, and the sample size is 25. So 50 over the square root of 25 is 5. The standard deviation is 10. We know 95% of the samples of size 25 that we would draw from that population would be within 2 standard deviations, 1.96 standard deviations below the mean and 1.96 standard deviations above the mean. So we know about that. That's what we know about. And if I go to a new population and I take a sample of that population and I assume that they have the same standard deviation, take a sample of that new group, and I say, are they really different from the population that I just examined here? Now, if I look at what the mean is for that population, let's say that their mean is 120, right? So their mean is 120. Well, let's see, 120, 30, the standard deviation, let's say it was 20, for instance, 30, it would be 1.5 standard deviations below the mean that I would expect for samples from this first population. Well, 1.5 standard deviations, that's not outside of that range where I would expect 95% of my results. Had it instead been 2.5 standard deviations, z-score 2.5, it would have been much lower than I would have expected for 95% of my results. So much lower that I would only expect to see that extreme a difference less than 5% of the time. And I can make a judgment. I can say to myself, you know, if it's going to occur, it's going to occur less than 5% of the time, I'm going to say to myself, well, that indicates to me, that's evidence enough for me to say that these two populations are different, right? So that's what we're doing. The z-score, we're testing how far apart two means are. But we're not using the actual means themselves. We're using the number of standard deviations apart that they are. When we know the population standard deviation sigma, we use z, right? Well, let's say we don't know that. We take a sample of 100 people. The mean comes out to be 150. The standard deviation for those 100 people, not the entire population they were drawing from, for those 100 people, the standard deviation comes out to be 20. Now, all that I've told you about samples so far is predicated on the fact that we know the population standard deviation. We absolutely know the variability of the whole population. In this case, we don't. All we know is the 100 people we sampled and how variable they were, right? So that variability, that standard deviation for that sample now is all I can use to represent the standard deviation of the population, right? So now that adds a bit of uncertainty to this whole thing, right? So since it adds a bit of uncertainty to what we know about the variability and what's going to happen with our samples, how spread out our sample means are going to be, now we have to accommodate for that extra uncertainty. Okay, and the way that we accommodate for that is we use a new version of the number of standard deviations. Instead of z, we call it t. And t is a new distribution that's based on the standard deviations, but on the ones that we measured from our sample, not the population. Since we're less certain about what the means are going to do, well, now I can't be nice if I have two values that are 1.96 standard deviations away from the mean below and 1.96 standard deviations above. I can't really be sure that that really represents 95% of the possible sample outcomes because I'm not sure what the real variability is. So in order to be 95% sure now, I have to move them apart. The number of standard deviations, the number of z-scores, in fact, now we're going to call it t-score, the number of t-scores, the number of standard deviations that I need to be 95% sure that I have all of the means has to be wider, has to be 2, 2.2, 2.3, 2.5. The smaller the sample size, the wider it has to be because I'm less certain about the standard deviation. That's why we use t. So when we compare a mean from one population to a mean from another population, as long as those two means are 1.9 standard deviations apart, if we know the population standard deviation, as long as the z-score for the difference between the two of those is 1.96 or larger, we can say we're 95% sure that they're different, right? Because we would only expect to see that big a difference less than 5% of the time. 2.5% on one end, 2.5% on the other end. With the t-score, if we don't know the population standard deviation, now we have to, based on our sample size, have a new number that we're going to use to be able to tell that they're really different with 95% certainty. And that p-value changes for every sample size. That's why we have a table that's based on sample size. We're talking about degrees of freedom. It's actually based on degrees of freedom, which is really the same thing as sample size, except -1. Are we okay with that so far? Makes sense? Okay, so we're going to calculate a z-score when we're testing for the difference between two means when we know the population standard deviation, but when we don't know the population standard deviation and we're getting our z-score from the sample, we're going to use the t-score instead, the t-table instead. Okay, so I'm going to try one example here, one simple example here, and we'll go step through it and we'll figure out what this means. And today, we're only working with a single sample t-test. We're going to take a known population we know the mean of, and we're going to take a sample from another group, and we're going to test to see whether that sample mean appears to suggest that that is from a population that's equal to the population that we know. So we got one sample and we got one known population. Okay, a coffee shop relocates to Italy. Sounds like a good idea. Maybe I might relocate to Italy. And wants to make sure that all the lattes are consistent. They believe each lot, they probably do research like this at Starbucks, right? They probably have a lab somewhere. They have a bunch of nutritionists sitting around, mixing flavors, testing that should it be 3.9 ounces of espresso or 4.2. They probably do this stuff, right? So she wants to make sure all the lattes are consistent and believes each latte has an average of 4 ounces of espresso. If that's not the case, then they got to figure out how to increase it or decrease it. They take a random sample of 25 lattes that shows a mean of 4.6 ounces of espresso and a standard deviation of 0.22 ounces. Okay, let's talk about that for a second. So that 4.6 ounces, what is that? Is that mu or X bar? Is it a sample mean or a population mean? X bar, right? It's a sample mean. How about that, let's see, the 0.22 ounces. Is that sigma or standard deviation? That's standard deviation, right? Because sigma would have been if we had every espresso that they ever made, right? Okay, so now we have two things we know. We know the mean of our sample size, three things. Sample size is 25, and our standard deviation for our sample. Okay, so next I'm going to say to myself, fine, okay, that's good. So now I want to compare to whether or not that's really equal to the average, the population average that everybody else pours in Italy of 4 ounces, right? So first thing I want to do is I want to write my null and alternative hypothesis. Okay, H null and H alternative. Okay, so let's see. First thing I'm doing is I'm comparing a known mean, mu, right, to my sample mean. Now remember, now that I'm talking about hypothesis testing, I know I'm only working with a sample, but in the hypothesis, I'm describing the relationship between the populations. So I always use mu, not X bar. So mu for our coffee shop, mu for a coffee shop is equal to mu for Italy. The mu for everybody in Italy, right? Which we know. What was the number of ounces in Italy? It was 4.0. We know what 4.0. We know that it's 4.0. That's the population. I could have just put mu Italy, right? Because it would be saying the same thing, but we know it's 4, so I'll just put the 4 in instead. And our alternative hypothesis is mu for the average ounces of espresso for our coffee shop is not equal to 4.0, right? Well, what did it turn out? I'm going to put down what we know so far. X bar is equal to, let's see, 4.6, right? So immediately we see, yeah, there's a little bit of a difference there. It looks like we're pouring too much espresso, right? And X bar and our standard deviation, our sample size, is equal to 25. And our standard deviation is equal to 0.22. Okay, so now the next thing I want to figure out is, I know my standard deviation for my sample, but now I want to know whether our sample mean is really significantly enough different than the mean for the entire population in Italy, whether or not it's different enough that I can say that the two populations are really different based on my sample, right? So now I have to calculate my standard error. And my standard error is going to be equal to sigma over the square root of n. I don't know sigma, so I have to use the standard deviation, 0.22 divided by square root of the sample size. Sample size is 25. I'm just going to put 5 in there. Okay, and that's equal to 0.04. What is it? 0.04, and 2 over 5 is 0.044. That look right to you guys? Okay, good. All right, so that's my standard error. So now what I want to know is my sample mean 2 standard deviations different from my population mean? And how do I set that up? Well, I set it up by saying, let's see, I'm going to set up a formula here, X bar minus mu, right, divided by the standard error. That'll give me the number of standard deviations. In this case, the standard deviation I'm talking about is not a z-score, it's a t-score, because it's based on calculating it from the population standard deviation. Yes? Standard error is the variability of repeated samples of the same size. In other words, a standard deviation, like for instance, if I took the weight of everybody in this room, right, their individual weights, right, would be used to calculate the standard deviation, right? The standard error is if I took a sample of size 25 of everybody in Hunter, and each time I took it, I took the mean for that 25 people, and the mean for the next 25 people, and the mean for the next 25 people. Is the variability of all the sample means. That's the standard error. Okay, that's the difference. Where the standard error, we're talking about sample means, how samples relate to each other. Standard deviation, we're talking about how population, individuals in the population react to compare. Okay, so what is that going to be? That is going to be, it's going to be equal to, okay, X bar is 4.6 minus, yes. Oh my goodness, when did that happen? And why does that happen? Sign into Chrome. Why all of a sudden did it wake up and want to do that? Okay, 4.6 minus the mean, 4.0, divided by 0.44, up 0.044. Okay, what does that come out to be? What does it come out? 13 point something, right? I'm going to call it just 13. Okay, that is your t-score, right? That is the number of standard deviations apart that these two numbers are. Okay, so now I got to say to myself, gee, that's very interesting. You'll see the formula up there too. T is equal to X bar minus mu over standard error, and the formula for standard error. Right? That's on the other side of it there. 13, that's a big number for a t-score. 13 standard deviations, that's ridiculous, right? That's an enormous difference because it was 4.6 compared to 4.0, right? So that is vanishingly unlikely to occur, that we would take a sample from our espresso group, our sample size 25, it would be remarkably unlikely to occur for us to find that for us to be having shots of 4.0 and then get a sample of size 25 that come back with an average of 4.6. So I can see right away that the probability would be almost zero here. Okay. Well, I'm going to change the numbers here to make it a little bit more likely. Okay. And I'm going to say to myself, okay, let's make it 4.1. Let's say the average was 4.1. Where is it? 4.1. And let's see, it's equal to 4.0. And this is 4.1. And this is 4.1. And this is 0.1 over 0.44. Can somebody calculate that for me? That's going to be 2 point something, right? Anybody working on that? 0.1 divided by 0.044. I'm sorry? 2.27? Okay, 2.27. Okay, that's my P. That's the number of standard deviation, standard errors apart that mu, which my x bar, my sample mean, and 4, which is the population mean for this other group R. There are that many standard t-scores or that many standard deviations apart. How do I know if that's enough to say that they're different with 95% certainty, with less than 5% chance of being wrong? Well, one of the things we set up here is that we want our, I think it's up here somewhere, run an sample the known population. Does it give you a alpha? I don't think it does. One of the things we're going to say here is that we want to have less than 5% chance of being wrong. In other words, alpha is less than 0.05. Okay? Less than 5%. So now we say to ourselves, okay, with a sample this size, what t-score do I need? How far apart do these means have to be for this sample size for me to be able to say there's less than 5% chance I would get that big a difference between the two of them? And in order to do that, I got to find my t-table. Okay. I use this Agresti one because it's the easiest one for me to find on my computer, usually. Yep, it's the same thing. Here we go. Then get it open. So how am I going to decide what my t-score has to be? What was our sample size again? It was sample size was 25, 24 degrees of freedom. So the first column gives me the degrees of freedom. So I go down to 24, right? There's 24. Well, which of these values I need to pick? Well, if I go up to the top here, a 95% confidence interval, or in other words, a value of 2.5% in each tail, 2.5% in this tail, 2.5% in the right tail, mirror image in the left tail. So an alpha of 5%, an alpha of 0.05, we have to have a t-score of 2.064. So what does a t-score of 2.064 mean? A t-point of 2.064 tells us that if we're 2.064 standard deviations below the mean, or 2.64 standard deviations, 2.064 standard deviations above the mean, 95% of the samples that we took, if we had taken samples in Italy instead of in this other group, 95% of those sample means would have been within that range of 2.06 below and 2.06 above, right? That's 95% of them would have been above there. So if we're outside of that, there's less than a 5% chance that we would go to Italy and do sample 25 lattes and get a value that's further away from the means. The means are further apart than that. So if I calculate a t-score from my sample and the mean for Italy, if I calculate a t-score that's bigger than that t-value, it means that there's less than 5% chance that the mean of the population, my population, is equal to the mean for Italy. So if the t-score is bigger than the t-value that we have there, there's less than 5% chance of being wrong if I say that they're different. Or in other words, if I reject null hypothesis. Okay, so can I reject the null hypothesis here? What was our value for t? 2.2 something, right? 2.26 or something like that. What's our critical value for t? 2.06. Our value was bigger than the critical value, so what can I do? I can reject the null hypothesis, and I can accept the alternative hypothesis. Okay, guys, again, a little bit more comfortable. We'll do a few more of these, and as we go along, you get a little bit more comfortable with each one of them, I guarantee. Okay, let's move on. Any questions so far? Okay, let's take a look at the next one. An inventor has a new energy-efficient lawnmower engine. He claims that the engine will run continuously for 5 hours, 300 minutes, on a single gallon of regular gas from a stock of 2,000 engines. He doesn't want to test all the engines. From his stock of 2,000 engines, the inventor selects a random sample of 50 engines for testing. The engines run for an average of 295 minutes. In other words, 50 of them, he runs them for an hour, runs a gallon of gas, they run 295 minutes. With a standard deviation of 20 minutes, is that so 295 minutes, 20 minutes standard deviation. Is that population or sample standard deviation in mean? Sample, right. So we're going to be using T. Why are we going to be using T? Because we don't know the population, we don't know the standard deviation for all 2,000 engines, only for our sample. Okay, so we're going to calculate T. So they test the null hypothesis that the mean runtime is 300 minutes against the alternative time that it's not 300 minutes. Not that it's more, not that it's less, but just that it's different than 300 minutes. Okay, so let's set up our null and alternative hypothesis. Okay, so mu for our test is equal to mu that is claimed, right? Okay. What is the mu that's claimed? 300 minutes, right? I could leave it like this, or I could just change this to 300. And that's our null hypothesis, that there's no difference between the ones we sampled and the population that he claims it is. H0. Okay, and my alternative hypothesis is going to be mu test is not equal to 300. Okay, so now what do I know? I know X bar is equal to 295. I know that my standard deviation is equal to 20. My sample size is equal to 50. And I'm going to calculate my standard error. What's my standard error going to be equal to? How do I calculate it again? 20 divided by the square root of 50. That I'm going to have to pull a calculator out for. Okay, let's see. 20. Oh, let me do the square root of 50 first. 50 minus the square root. That's wrong. Let me clear everything out first. 50 square root. That's it. Okay. And 20 divided by the square root of 50, I get 2.82. 83. I'll take your word for it. I erased it. I don't remember anymore. Okay, so 2.83, that's my standard error. Okay, so now I have to calculate whether or not my mean for my sample and my mean for my population are more than the number of standard deviations apart that I need to reject the null hypothesis. Well, before we do anything else, I'm going to look up what t critical is. How big a t-value do I need to have in order to reject this null hypothesis? Okay, so what was our sample size this time? What happened here? Our sample size was what? 50. So I'm going to use 49. There is no 49, so I'm going to stick with 50. And I got to use this column here for 95%. Half of t is, half of the alpha is 0.25%. So for 95% confidence, right? Let's see, 50 is going to be a value of 2.009. I'm going to be a little bit more conservative since I don't have 49, and I'm going to call it 2.01. Okay. So my critical value of t that I need to exceed is 2.01. If we had known the population standard deviation, what would the critical value have been? We would have used z. What would the critical value for 95% be? 1.96. See, that's the whole deal. That's why we're using the t table, because it makes it more demanding for us to reject the null hypothesis. Okay, so let's do this. Let's see. T critical is equal to 2.01. Okay, so now let's calculate what t is. So t, let me find a good place to do this. I'll scroll up a little. T is equal to x bar minus mu divided by the standard error. Okay, so let's see. T is equal to 295 minus 300 divided by, what was it? 2.83. 2.83. Okay, what does that come out to be? How much? 1.74 was that? Negative 1.74? Negative 1.74. The sign doesn't mean anything. Sign just tells us whether it's below or above the mean, right? Still got it wrong. What was it? What was the number? I'm sorry. 1.74. Is that what I wrote? Yeah. Yeah, okay, good. Okay. All right. So 1.74. What was our critical value of t? How far apart did they have to be? They had to be 2.01 standard deviations apart, 2.01 t-scores apart. How much are they? 1.74. Are they far enough apart for us to reject the null hypothesis? No. So what do? We fail to reject the null hypothesis. Have we proven the null hypothesis? No, we haven't done anything with the null hypothesis. We've just failed to reject it. In fact, chances are the null hypothesis is false anyway, because we got pretty close to rejecting it, right? This might only occur 10% of the time instead of less than 5% of the time, right? So we don't accept the null hypothesis. We just say either we fail to reject the null hypothesis, or we reject the null hypothesis and accept the alternative hypothesis. There's a question back there. 1.77 was it? Okay, good. I'll change. Same result. Yeah. It doesn't matter. It doesn't matter, because remember, the idea here is that you're looking for a difference between one population mean and some other population's mean. So when it's a two-sided test, you don't care if your result is 2 standard deviations below or 2 standard deviations above. You only care that it's different. So if you get a t-score, in this case, if you had a t-score of 2.1 or larger, you would have rejected null hypothesis, whether it was negative 2.1 or positive 2.1, because you're only interested since it's a two-sided test. In other words, the alternative hypothesis is only that they're different, not that it's less than or greater than, only that it's different. It could be a negative it could be negative or positive, as long as the amount is big enough. Right? Make sense? Okay. 99% of the time, you're going to be doing two-sided t-tests. You're not going to care about the sign. Right? The only thing that determined the sign was the fact that I subtracted the 295 from the 300, rather than the other way around. Okay, let's do another one. How are we doing on time? Okay, not great, but good enough. Oh, did I just close that? Is it still there? Did I close it? Or did I just make, oh no. What is this thing doing now? Oh, there it is. It's still there. Okay, the next one. This one you guys are going to do. Okay, you're going to do it one step at a time. Bon Air Elementary School has 1,000 students. The principal thinks that the IQ of students at Bon Air is 110. They all think the kids are smaller than everybody else's kids, right? So that's pretty much the. But you guys ever listen to the Prairie Home Companion? What was the name of that guy that on the radio used to do that? Like it's about this little kind of like semi-imaginary place in North Dakota or something like that. And one of the taglines is that all the all the all the women, I forget, all the men are something, all the women are this, and all the children are above average, right? So kind of doesn't make any sense, right? I mean, how can all the children be above average? But that's kind of the case here. So the principal thinks is the average IQ of students at Bon Air is 110. To prove her point, she administers an IQ test of 20 randomly selected students. Among the students sampled, the IQ is 108 with a standard deviation of 10. Based on these results, should the principal accept or reject her original hypothesis? Assume it's a significant level in alpha of 0.05, and assume the test scores in the population are normally distributed. Okay, so you're going to set up a null and alternative hypothesis. You're going to calculate your standard error. Calculate your standard error. You're gonna calculate your statistic. In this case, your statistic is a t-statistic. And then you're actually, let's look up the critical value of the t first before you calculate it. Okay, so you have it handy, and then you calculate t statistics, and then you're going to figure out your conclusions. So the first thing you need to do is set up your null hypothesis. So I'm going to let you guys do that. I'm going to just kind of fill this out a little bit. HO equals, okay, and HA. Then you're going to calculate your standard error. I'm just going to remind you that the standard error is equal to the standard deviation divided by the square root of the sample size. And then you're going to look up your critical value, right? It's alpha is less than 0.05. And that's also the same column as a 95% confidence interval. Okay, and then you're going to calculate, you're going to look up the critical value, critical at t critical equals, you calculate your t statistic, formula there is going to be t is equal to x bar minus mu, minus mu over standard error, and you're going to compare it to your t critical. Okay, so let's do them in sequence, so that as you work on it on your own, you can kind of go through it step by step. So I'm assuming that you guys, as I'm typing that, you guys are working on the null hypothesis. So your null hypothesis is going to be mu, right, for what school is this? Bon Air, is equal to the value he thinks it is for all, that he thinks it is 110, right? And your alternative hypothesis, mu Bon Air, is not equal to 110. Did everybody get that? Is that okay so far? You guys comfortable with that? Okay, mu IQ. Yeah, you can use mu. Yeah, mu IQ. It might be a little bit better to identify the group that you're talking about. It's like, in other words, the mu for the Bon Air students is equal to 110. A mu for Bon Air is not equal to 100. That's not so important here because it's a single sample test, only one sample. Next time after the test, we're going to be working with two samples. Like, in other words, we're going to take 25 students from Hunter and 25 students from a city university, a city college, and we're going to take IQ tests for the 25 students, and we're going to compare the two means. In that case, it's going to be mu Hunter is equal to mu CUNY. So you have to identify. Here, it doesn't make that much difference because only one, right? So I'm only sampling the Bon Air students. But it's good to get into that habit, maybe. Just give it a little ID. Don't go nuts. Sometimes you put too much information in there and you just go off track. Okay? So that's what I would put in as my null and alternative hypothesis. Okay, so I'm thinking you guys probably calculated standard error by now. So I'm going to do that now. It's going to be equal to, okay, what's it going to be equal to? Well, the standard deviation of I don't know the population standard deviation, but the standard deviation for the sample is 10. So it's equal to 10 divided by the square root of the sample size. Sample size is 20. Okay, so let me get my calculator out. And normally I'd use, if I'm going to do this by hand, I'd probably use Excel. Right? A little easier to deal with it that way, but we use a calculator. So 10, square root of 20, I'm going to do that first. 20, square root of 20 is 4.72. I'm going to put that into memory. I'm going to clear it. Then I'm going to say clear. Then I'm going to say, where is it? What am I looking for? 20, no, 10. 10 standard deviation divided by the square root of the sample size, recall memory, is equal to 2.24. And I am cutting a couple of decimal places off here because I'm in a little bit of a rush. I want to get through as much of this as I can. All right, so standard deviation is equal to 2.24. So now I need to know, okay, standard error is that. Now what's the critical value I need? The critical value that I need for T critical, has nothing to do with anything else. It only has to do with the probability, the chance of being wrong I'm willing to accept. In this case, it's 5%, alpha 5%, and the sample size. Only two things you need for that. Don't need any of that other information. Okay, so this sample size is 20, so 19 degrees of freedom. And for 19 degrees of freedom and alpha of 5%, it's 2.093. So now I have that. Now I know that my t-value, the distance apart, my mean for my sample, which was 108, and the true mean, which is 100, and the comparison mean, the population mean that he hopes for, which is 110, that they are at least 2 standard deviations, standard errors apart. Let's see if they really are. So t is equal to x bar minus mu over SE, so that's going to be equal to 108 minus 110, and it's coincidence that it's negative again, okay, over 2.24. I almost confused myself there. Okay, and that's equal to 0.8, what was that? 80? 89. Okay, 2.89. Okay, so does our t-value exceed the critical value of t that we need? What was the critical value of t? Yeah, so do we exceed that? No, I left out the minus sign, but again, it doesn't matter. So since we haven't exceeded t critical, what can we say about our hypothesis? No, we don't reject it. You fail to reject. You don't say you accept it. You say you fail to reject. Yeah, I know it sounds semantic, right? But the deal is that the way this is set up, the only thing you can really say, because of the way this is set up, is whether or not you can reject it, right? In other words, whether or not they're different. That's the way this is designed. So since it came out to be our t-value came out to be 0.89, and we needed to exceed a critical value of 2.09, we failed to reject the null hypothesis. Okay. Now, what if the value that the 20 students that he had tested, what if they turned out to be not 108, but instead of 108, they were 100. Well, in that case, it would have been 100 minus 110 divided by 2.24, and I'm guessing that that is roughly 4 point something. 4 point. I'm going to call it 4.2. 4.46. Thank you. 4.46. Can I reject the null hypothesis now? If the t-value I calculated is 4.46 and my critical value was 2.03, can I reject the null hypothesis? Yes, now I can, because my t-value exceeded what I needed. They're far enough. They're 4 standard errors apart, not 2 standard. They're not 1 like before, but now they're 4 standard errors. So they're so far apart, I can have enough confidence to say I can reject the null hypothesis. Okay, so in this case, we would reject the null hypothesis. Before I change to the 108, you would fail to reject the null hypothesis, right? Because they just weren't far enough apart. And it makes sense, doesn't it? In other words, if this guy, if you're at the NFL Combine and this player runs the 40-yard dash in 4.3 seconds, and the player next to him runs it in 5.5 seconds, you say, well, that guy's a lot faster than the other guy. But if this guy runs it in 4.3 seconds and the other guy runs it in 4.31, now you say, hey, maybe that guy, got off the blocks a little slow. Maybe they're not far enough apart. So you want things, in order to be sure that you can say that they're different, you want them far apart. That's what statistics is all about. Now I'm going to do one more thing here, and that is there's a document, there's a file here on Blackboard, and I'm just going to do it myself and get this stuff out of the way. And that file is called Sample Dataset 2. And actually, at the end of that document, I'm going to open it up. It's an SAV file. You also have an Excel version of it. We're going to go over this a bit next week also. The week after. And I'll give you, before we take the test next week, I'll do at least one online session. So you guys can write in questions. I'll give you some more examples. Okay, come on, start up. There we go. Actually, I want to open that Word document again. The data set that I'm opening up goes along with the last problem, I think, on this set of problems that we just went over. Come on, no beach ball. Okay. So again, we'll work our way back. Okay. Okay, according to CDC, the average height of adult males is over 20 is 66.5 inches, 69 inches for male. Let's test to see if the mean height of our sample data is significantly different from the mean height of all adults, according to the CDC, 65.65 inches. And our mean is, we found was 63.8 in our sample, right? So we have our data set open, and one of these is height. See if we can't find it here. Here you go. Here's height. I just got away from me there. Wait, here's height, right? So we have heights for a number of students. I don't know. Let's see how many. Looks like a few hundred, right? We have a few hundred, sample size of a few hundred. So now if I want to do a single sample t-test, I go to Analyze. I go to, what am I doing? I'm comparing means. So I go to Compare Means. And I go here to one sample t-test. I have one sample. I'm comparing it to what the CDC says is the population of the entire country. So let's see. I'm going to test the variable height. So I'm going to move height into this box, right? So SPSS is going to calculate the average for my 400 students, the average height, and the standard deviation for my 400 students, right? So it's going to calculate both. And since it knows the sample size, it's going to calculate standard error. It has all it needs in order to do a t-test, just the same way that we would. Okay, except now it needs to know, what am I going to compare it to, right? Well, my sample mean is 62.5 or something like that. But the population mean supposedly is 66 or something like that. I forget what it was, 66? So what I got to put in here, I got to put in 66. So in other words, I'm telling SPSS that the value I wanted to compare it to, the known mean, is 66. So our mu height is equal to 66, or our mu height is not equal to 66. That's our known alternative hypothesis. So I'm going to go ahead and ask it to do this. I could have gone into options and told it the percentage. It defaults to 5%. Okay. Now let's see what we got a result for a t-test, and it says that the mean for all of these people is 68 inches. The standard deviation is 5.32. The standard error is 0.326, and the t-score is 7.706. I'm going to go back and do this again. And the reason why I'm going to do this again is I want to get it closer. So there's a, most of the time it's static if there's a big difference and you get a big t-score, because that means you're very confident, right? But I wanted to get another look at this. I'm going to say 67.8. I'm going to say, okay, that's what it's going to compare it to now. So you put the value you want to compare it to, that what the t-score is equal to. This time my t-score came out to be 0.879. Do I reject the null hypothesis? No, I don't, because it's so small, right? Well, I did not look up the critical value of t. So how do I know that? I know this one because it's so small. But how would I have known if it were closer? Well, if you go down across here, you will see that there is also, SPSS also calculates a two-tailed significance. That is a p-value, a probability that you would be wrong if you reject the null hypothesis. So we need that value, that p-value. In other words, that's 38% is how often you would get that result. If there were no difference in the two groups, we need that to be less than 5%. So if that p-value, that significance two-sided, is less than 0.05, we reject the null hypothesis. If it's greater than 0.05, we fail to reject the null hypothesis. So at 38.38, 38%, we fail to reject the null hypothesis. What's that telling us? It's telling us that if we reject the null hypothesis, there's a 38% chance we would be wrong. I'm going to do it for one more value. I'm going to change it from, what did I use the last time? The mean I used was analyze, compare means, one sample t-test, 67.8. I'm going to make it 67.5. Okay. Okay, and it solves it again. This time, my t-score comes out to be 2.017. What do I need to know can I reject the null hypothesis now? Well, if all I know is the t-score, I need to go to the t-table, see what the critical value is, to see if 2.017 exceeds my critical value, right? Well, actually, we don't need to do that with SPSS. SPSS will automatically look up not just whether it exceeds the critical value, but give us an actual percentage of probability we would be wrong if we reject the null hypothesis. We want less than a 5% chance of being wrong, right? So if I go over here, the probability of me being wrong, the significance two-tailed, is 0.044. There's only a 4.4% chance I'll be wrong if I reject the null hypothesis. Since I'm willing to accept up to a 5% chance of being wrong, I can reject the null hypothesis. Okay, so in this case, when we use SPSS, we don't have to look, it gives us the t-value, but we don't have to go to the reference table for the t-score to see how they compare. When we do it manually, we have to do that. So in this case, SPSS gives us that value. Okay, you guys okay with that? If that number is less than 5%, you reject the null hypothesis. That's the probability you would be wrong if you reject the null hypothesis. Since it's less than 5%, you're willing to accept 5% chance of being wrong, making an alpha error. Remember, alpha is equal to 0.05. Now, you're willing to accept a 5% chance you're wrong when you reject the null hypothesis. But find the innocent guy guilty. That's the null. That's alpha. You're willing to accept 5% chance of that, right? So sometimes if it's really important, you may not want 5% chance. You may want 1% chance of being wrong. So in this case, we would not reject the null hypothesis.